And so you mentioned mass spec. I mean, we'll go do a deep dive into that and the company in a second. But for those listening who may not be familiar with kind of what the tool is, what it does, just the general science behind it, what can you give us a quick 101?
Yeah. So we'll just do mass spec in general. We can talk about the mass box
Yeah,
later, and kind
perfect.
of what we do differently. But a mass spectrometer is just a tool that we use to separate out mass, right? So a mass spectrometer, we're creating a mass spectrum. And the key components to it are you need to have a source. So you need to have some way of taking an atom or a molecule, introducing it, and then ripping off an electron or giving it an extra electron. And so that's what we call the ionization source. So there's a lot of different ways to make ions, whether it's with lasers, with chemistry, with high voltage, lots of different things that we can do to basically give an atom a charge. The reason we have to give it a charge is that once it's charged, we can interact with it with an electromagnetic field. We can talk to it. We can push it around. We can focus it. We can speed it up. We can slow it down. And what we want to do is we want to take all of those atoms that we've ionized. So let's say it's a mixture of carbon and iron and tungsten. We want to be able to separate those out because at first they're all just going to be just glob of ions, but we need to separate them out somehow and count them. And that's really what the mass spectrometer does. There's a lot of different techniques. Some are as simple as what's called a TOF, which is what we use, time of flight. So if you kick all of those atoms with a high voltage at the same time, it's like kicking a bowling ball or a soccer ball. The soccer ball is going to go very fast and the bowling ball is going to go slow. And if you kick them with the same force. And so the same thing would be true if you kicked hydrogen and uranium at the same time. Hydrogen goes really fast, uranium goes very slow. So if you give it enough time to separate and you have like a recorder at the end of the line, you'll see a hydrogen peak. And then some microseconds later, you'll see a uranium peak. And basically, you can get the whole spectrum this way. So that's called time of flight. There's other techniques which uses magnets to separate them out, like they'll deflect more or less in a magnetic field, or using rods to some really, really clever voltage games that you can play with RF frequency to separate out mass. But essentially, it's separate out mass, count the different masses, and do it in a way that is hopefully quantitative at the end of the day. I had 10 parts per million. I had 10 weight percent, right? Having a metric to say it's not just in here, but it's in here by this amount.
Yep. And and the reason you would want to do this is you want to know what's in a given material, or if you're looking at new materials, you want to sense, okay, what's this composed of? How can I use it? How much of it is it contaminated? And some of those types of use cases.
Yeah, exactly. So if we stick to the inorganic side, since we'll probably talk a lot more about that, so just periodic table elements. Yeah, whether you're reverse engineering material, you're doing R&D on something, or you're doing quality control, it's way more important now, now more than ever in the world to really understand the chemistry of the new metals we're making, the new ceramics we're making, or the hybrid of the two. All of these different things, we want to know down to the parts per million how much carbon and oxygen are in there, how much tungsten, and correlating that with, let's say, the strength tests that you're putting these things through and getting a much better refinement on that material characterization. And currently, there's a lot of lacking in this. It's much more qualitative a lot of the time on chemistry because it's very difficult to do. You can either do kind of qualitative fast analysis with spectrographic tools that are kind of looking at, let's say, like x-rays or light emissions from the
Yep.
samples, or you can do digestion and go through mass spectrometry and get really good answers, but 4 to 5 week turnarounds and $1,000 per sample to get all the elements you want. It's kind of this dichotomy. And that's kind of where we sit right in the middle.